it just needs these two things here. Okay, so that's how it looks like. This is the one. And again, let us call the frozen. Okay, what do we see here now? I have started a measurement with AC voltages as an input to this resistor, and these AC voltages have different frequencies. It's a little bit small, but you can see, or you maybe can see that, the frequency here on the axis. So we start with 100 Hertz. This is 1 kilohertz, 10 kilohertz, 100 kilohertz, and the blue line here then is the impedance in ohms. Okay, so this is 10 ohms, quite small. Then let's change the value a little bit here. No, it doesn't do anything. Okay, yeah, that is. Okay, I told you, I did not try this before, and well, let's see. Okay, but the result has something to do with the measurement, obviously. And this is now a demonstration of engineering. Engineering is actually just looking for errors most of the time. Okay, the error is that I shouldn't look at the blue line, I should look at the red line. So let's delete that. Yeah, so this is the one. Okay, this is the real resistance for different frequencies. So it doesn't matter which frequency the AC voltage has, the AC current is always in phase, it's always happens at the same time. And we have a resistance here of about 670 ohms. You can change that, you can make it smaller or larger. Okay, but it's the same for all frequencies. Yeah, this is what I said. The ratio of voltage by current is always constant, and that is valid also for AC signals. Yeah, really. So let's increase this. We see frequencies up to 100 kilohertz here. Let's say now up to 1 megahertz. Okay, it's still valid up to 1 megahertz here. Everything is constant. The resistance is the same. So should we stop here? No, let's go up to 10 megahertz. And here something happens. So for higher frequencies, it's not very, very high. It starts with 2 megahertz. The resistance becomes smaller for some reason. And there is also a phase included, and that means voltage and current are not in synchronization, but they have a time shift between them. Let's look at the phase. Yeah, this was now trace number 2. This is now the blue one. Here, for a large range of frequency, the phase is 0 degrees. That means there is no time shift between voltage and current. But here, now for these higher frequencies, there is a shift, and well, why is that? It cannot be described by the normal or the simple model of the resistor alone. Okay, and that is because we have we have in the real resistor here. I scratched away the lacquer so you can see what is inside the resistor. The black tube does not conduct, but on its surface you see like a coil. Okay, so this is a conducting metal layer here that makes up the resistance, but it's also a coil which produces inductivity. It produces a magnetic field, so it has an inductivity. And it seems that we can model this again with an ideal resistor and a serial inductivity. But that's not all. You see something more here. On the left and right side, there are clamps, fat metal clamps. And these two clamps, they act like a capacitor. They're just like the plates of a capacitor. So we can model this with a parallel capacitance. And actually, it was this capacitor, or the effect of this capacity, that we just saw, because for higher frequencies, this becomes an ever smaller and smaller resistance in parallel. So the total resistance is reduced for high frequencies, and that was what we saw. Okay, so that means here we have a better model. So we have to adapt first the simple model. We have to find a better model, but it's still much simpler than the real physics. It still does not comprise all of physics here. But this is a model that is suitable for most situations. And we will see that we can also cover other situations, not only electric components, but for example, mechanical systems or heat transfer and everything. Also in the form of concentrated elements. Concentrated means the space does not play a role. Okay, so it doesn't matter how long the resistor is. So these are three concentrated elements, and you can nearly model the whole world as just a schematic of concentrated elements. That's true as long as we have not very fast oscillations. An oscillation means we have a wave. So that means some quantity, for example, an electric field, changes with space. So here we see, for example, a distribution of electric fields in a cable here. Okay, if the dimension, any dimension of an object is larger than a wavelength of any quantity, then we can not use this approach. And then this course is at an end. Then you will have to switch over to another method, which is called finite element method, which looks into the components and into the spatial distribution. So that's something for the other course, micro electromechanical systems. I don't know if some of you also go there. It's offered on Thursday. Okay, so this is the limit, so we will not talk about this, so that means we will always have smaller dimensions, and our wavelength is always smaller. Now we have large dimensions. Okay, now back to the system. Well, the system, it can be described with signals. It's just time functions. We have an output signal, we have an input signal, at least one of them. And in the system there might be something with a memory, for example, something that stores energy, that's like a memory. And that means the path or the change of signals has an influence on the output. Not just the current value, but also what happened in the past. Okay, we can describe all the systems with differential equations. Simplest example is the output function, the y, and its derivative, the first derivative in time, have an influence. And when I build the sum here, so I add up the signal and its first derivative, I need another constant here. I need here a constant. and you can see what the meaning of this constant must be. It is a time. It must be a time. And why is that? Why can I say, no matter what the system is, I didn't talk about it, but why must this be a time?
Is the signal in respect to time? So x and t.
So we need the same units, yeah, that's right, we need the same units for both terms, and no matter what unit the y has, this term is this unit divided by seconds because of the derivative, so we have first to multiply it again with seconds, and then we can add the two quantities. Okay, so that means I know this must be a time, I don't know what's behind it, but this must be some time. Okay, and this is connected then with the input. X is the input function, and there could be just a constant, a variable. This variable also could have a unit. For example, you could say the resistor as such is a system. The input to the system could be then the voltage which is applied by a device, and the output of the system is the current which flows through the system. So why would then be the current? That's the voltage, and it does play a role. It does play a role what happens in the past if we use high frequencies. Okay, for a unique solution, we need to know something more. Just one value for the output at any time, for example, at time 0. That must be known, otherwise we get infinitely many solutions. Okay, examples still from the electrical world. We have two components in parallel. So this is an R and a C. And then we have here a source, a current source, which produces a constant current. And before we can do anything, we have here a switch, which is normally open, but at time 0 it will close. So what happens then after time 0? First of all the individual components have their own laws, have their own equations. So for the capacitor, we know there are charges on it, and the number of charges is proportional to the voltage, which we can measure on the capacitor. So this is the voltage U here in blue, okay, measured between top and bottom. Proportional, and the constant is called the capacity. So this is then our element equation, and let's say before closing the switch, this capacitor was empty, so the voltage at time 0 was also 0 volts. Let's go one step further. If we change the number of charges, so that means we have a derivative in time, that's nothing else than the current which flows in or out of the capacitor. So this is the current IC, which is drawn here downwards. Okay, so the capacity, of course, is always constant, so it's just C times the derivative of the voltage, and this now is the component law, but that describes only this one component. With another component law for the resistor, okay, we know that that's Ohm's law, so the current is just voltage divided by R. Let's say it's a simple resistor. And now we need something more. We need one equation which combines all the elements of this system. So we have to find something which is in balance. And we can find that all over the world for any given system, for any situation, there must be some balance, some kind of balance. In this case, we can use the node, and we know that currents in a node are balanced. That means the sum of all currents must be 0. Or we can write it in another form. We can say, I have drawn here two currents which go out of the node, so from top down. And there's one current which will flow into the node. That means the two component currents are equaled by the source current. Okay, so that is the basis for a differential equation, because when we now insert the individual component laws, then we find here the voltage divided by R plus C times the derivative of the voltage. That yields our source current, and we have a differential equation for the voltage. We could stop there, but there is a normal form, it's called normal form, if the quantity we're looking for has no factor. So if it just stands as u times 1 in this case, and that means we have to multiply the whole equation with R. So this is now the differential equation in the normal form. Okay, R is the resistance, C is the capacity. R times C must have which unit? R times C. I mean, R, okay, that's ohms, the unit, we've heard about that. For a capacity, it's farad, but farads, well, what is that again in SI units? But no, we don't have to know it. It's not necessary. R times C is nothing else than our constant tau from the last page. And we said this must be a time, because here we have voltages divided by seconds. Okay, we do voltages by seconds, and we want to add this to simply volts. So we must first multiply this with the seconds. So R times C must have the unit seconds, and this here is constant tau. And then we can say, okay, this current here, this is the input signal x, what we call x, and that means the multiplication with the R. That's what we called the constant K on the last slide. Okay, another example, again, how to find a balance. But first of all, it's similar, but nonetheless a little bit different situation. We have here now three serial components. And again, we have a source, in this case it's a voltage source, and we have a switch which closes at time 0. Before, when the switch is open, we say the capacitor again is empty, so there is no voltage across it. We have no current, so also the voltage through the resistor is 0, and also through the inductivity. But when we close the current, well, what happens then? Okay, first of all, each component has its own law. We already know what happens at the capacitor. Okay, so that's the same as before. For the resistor, we know, again, it's Ohm's law. For inductivity, well, this is the law of inductivity. So if you change the current through it, you get a proportional voltage. Okay, and then we know something that combines all elements, that describes the whole system now. This is the basis for our differential equation. The sum of all voltages in the loop is 0. Or again, we can say this a little bit different. Going here from left top to bottom, okay, so here around, this is exactly the source voltage U0. But there's an alternative path, so we can go here from top left, can go over the capacity, then over the resistor and over the inductivity, and also arrive here at the bottom. And when we go over several voltages, we have to add them. So the sum of these three component voltages equals the source voltage. That's the basis here. To make it more easy, let's build the derivative of this equation. So then we have here first term, derivative of UC at the capacitor. We can replace this with the current divided by C. So that's the first one here. The second one, also a derivative of UR. Okay, this is then now R times the derivative of the current. Sorry. That's the second one. And the last one, we have not UL, we have the first derivative of UL, but then that's already the second derivative of the current. Okay. And then we get here the differential equation, in this case for the current through all the components. It's the same for every component. And this is what it describes. Again, the normal form is when the quantity you are calculating has no factor, so if the current stands alone or times 1. So again, we can see here, okay, we have the first derivative, a division by seconds. So we find again here R equals C, which is the time constant somehow. And then we have another term here, L times C, which unit must have this L times C. Seconds. Yeah, nearly 1 over seconds squared. And no, you're right, seconds squared, sorry, it was seconds squared, yeah. What I was thinking about is L times C is normally, if the system starts oscillating, then the resonant frequency, or the frequency of this is then has to do with 1 over the square root of LC, but we will see that in a moment. Okay. So some examples of differential equations. We could increase the order, so we have 3rd order, 5th order, 10th order differential equations. We do not have to cover everything because every very complex system we can always decompose into either systems of 1st order or serial 2nd order systems which have oscillations. And for these 2nd order oscillating equations, there are some special parameters. So here the factor for the first derivative of the output, it's not just one time constant, but of course the unit is seconds, but it's a more complex term here, which includes 2 parameters. D is just a value and describes the damping. So how much damping is inside this. It has no unit, it's just a number. It's always positive. Well, if it's 0, then you have no friction, no losses, nothing at all. It's just an ideal state. In reality, it can never happen. But okay, so D is always larger than 0. If it is also smaller than 1, then this system can oscillate, can produce oscillations. And these oscillations then are around, let's say, around the frequency omega 0. And we have seen that when we compare this with the last slide, this 1 over omega 0 squared. It has to do with L and C. Okay, so what happens if D is larger than 1? Then we can decompose this 2nd order system into a series of 2 first order systems. And then we don't have to look into this anymore. So this would be an alternative form here for a 2nd order system. And here you can see 2 different time constants, one for the first system, one for the second. So you could understand it like this. We have an input, x, then we have here the first system with tau 1, and then we have in serial second first order system with tau 2 and k2, and here we have the output. And okay, tau 1, tau 2, this is here from the equation, and the two k's are arbitrary, so you can define them how you want, but the product k1 times k2 must be this complete k from the equation. Okay, and if you have a 10th order system, then you can be sure it's a long log series of either these first order systems or oscillating second order systems. Okay, let's try to produce one of those. I have some more components here. So this is an inductivity, obviously, a coil, and then we put there a serial capacity, and then a serial resistance. I hope it's small enough. The resistor is the thing that makes here damping. So this is responsible then for the D. And okay, now we can analyze this. Okay. First of all, the total impedance in the system, that means the sum of all elements, sum of all the resistances, let's say, of these three components, the same. So you see, okay, let's go back to smaller frequencies, let's say 1 megahertz, okay, because we have seen after that we get real effects. Okay, up to 1 megahertz we can say all the components are approximately ideal, and the total impedance here has a minimum. So for small frequencies the resistance is high. But here think who's responsible here? There are a few components. Why is the resistance high when we have slow oscillations, or if we have here a DC? Why is the resistance high? Well, the R is always constant. So it says here 47 ohms. So that's not the responsible one. That's always the same value. The coil, well, this is just a length of wire. The resistance is very small. So if we push a DC current through it, well, the resistance is close to zero. So it must be a capacity. And in fact, yeah, that's the problem, because we have two metal plates and they are isolated, so no DC current can flow through a capacitor. So that makes a high resistance. And for slow oscillations, okay, you can get an AC current through a capacitor, but then it's a small current, and that makes a high resistance, or let's say a high impedance, it's called. But this impedance depends on frequencies, and that means it's smaller for higher frequencies. Then we get a minimum, and then the resistance rises again. Sorry, this is a bit confusing. Okay, so this is just the resistance as such. Well, it rises now because the coil, the inductivity, has an increasing impedance, so it's it does not want the change, you could say. It has produces a high voltage if you try to change the current very fast, and that means it has again a high impedance. Well, and the minimum is the value. Let's search for this value. about 48, 47 ohms, and that is not by chance the value which is printed on this R. Okay, so there is a minimum value, and that is defined only by the resistance, and somehow the effects of coil and capacitor cancel each other out for this one frequency. Okay, but we were talking about systems. In a moment we can talk about voltage dividers, but at this point let's still talk about other things. Well, if we know how the system is built up, then we can try to find this differential equation, but if it's a closed box, if we cannot look inside and we don't know what components are there, we can still try to find the kind of system it is. That means which order of equation, of differential equation it is, by testing it with an input function. So one possibility is that we test it with a step at the input, means the input is changed at once, from one constant value to the next constant value. And we know for first order differential equation system, the output will follow with a delay. So this is the input in red, the output in blue. So it will follow with a delay, and after some time, which has to do with the tau from the differential equation, we will get close to K was the let's say sensitivity constant, but also from the differential equation. Okay, this is the K, first order differential equation. So K times the input, and the output will be close to that. For a second order and oscillating system, the step response is a bit more complicated. We see here an oscillation. The frequency is not exactly the omega 0, it's normally smaller than omega 0, but it's in the order, it's around omega 0. And it's a damped oscillation, which has to do with the damping D. So in this case, the resistor, for example, is responsible for the damping, and you will also get a damped oscillation. Okay, that's one possibility to test a system and see is it first order, second order. You can also see higher orders. But technically it might be difficult to implement a perfect step at the input. So sometimes you need something else, and what will always work is when you have a sine wave at the input. You will have to switch it on, okay, but then you have a sine wave at the input. After some time, which is called the transient time, then you will also get a sine wave at the output. And it will have exactly the same frequency, always. But what is different for the output is the amplitude, that might be smaller or larger, and there could be a time shift between the two oscillations. For example, here we have it's nearly an inversion here already, nearly. But it could be any time shift. And that has to do with the phase, because the output is then always also the sine wave, the sine of omega t, and we can include here this phase. Okay, so you test your system with this oscillation, but not with only this one, but with many, many different frequencies. And then you can put together two diagrams. On the horizontal axis, you find the frequency, or you have to put the frequency. And on the vertical axis of the first one, you have the ratio of the amplitudes. And on the second one, you write the phase of the phase between the two oscillations. And this is now typical, here a typical diagram for a first order differential system. How can we interpret this? Okay, for low frequencies, that means on the left side, here left or here left. For low frequencies, the frequency shift is always close to 0, and that means voltages and currents are in phase. Not only voltages or currents, input and output are nearly in phase. Means if one has a maximum, also the other has a maximum. If one has a 0, then also the other has a 0. Then as for the amplitudes, they are governed then only by the factor k. So that means the output will just be the amplified input amplified by the factor k. And for higher frequencies, then the ratio of the output typically becomes smaller if it's a so-called low-pass system. So it might be smaller. And at the same time, there will be a phase shift between input and output signals. It means phi is not 0, it becomes, for example, changes here between 0 and minus 90 degrees. Okay, so this you could derive by experiment, by measurement. Let's try to measure again. And here I use, okay, first we use this resistor and the capacitor here. We use that as a system. And well, the same machine, which measured until now only impedances, only resistances in ohms, can also measure a system. We use this now just as an input to both components, and then I need more cables. Or let's say this is just for excitation. Now the next cable, this defines where is the input of the system. I put that in parallel. That means exactly where I excite the system. This is also the input. And the last cable, this defines the output. And let's say we are going here just on the capacitor. So we measure just the voltage of the capacitor. That is the output variable. Okay, then I have to switch over here. Yeah, okay, and this is the left diagram which we saw in the slide. So the device makes measurements, and in fact we see here a ratio of amplitudes at the input. So this is the voltage here at the input across both elements, and the output is then the voltage only across the capacitor. For low frequencies, it's the same. So we have here units, dB. Are you familiar with decibels? Okay, if not, then you can change this. We can just say, okay, show us the magnitude in values logarithmically and optimized. Okay, so the ratio is 1. That means we have always exactly the same amplitudes between the whole input and the output. But for higher frequencies, the output voltage becomes smaller and smaller. So this is the left part of the diagram that we saw, and this is typical for a first order system. You can also watch the phase in blue. Okay, so let's also optimize this. Okay, in blue, and the phase axis is here on the right side. No, this is something completely different. We need gain phase. Okay, now again optimize. Okay, now it's the phase. So this is the axis for the phase. It starts with 0. It means, okay, really for small frequencies, we have no phase. It means no shift, no time shift between AC voltages at the input and the output. And for high frequencies, we go up to approximately minus 90 degrees. So it's really just like the prediction was here, or what it showed here. So that's typically for measurements of first order systems. By the way, it might take a long time to measure all these because, for example, here in this case we have, what does it say? Yeah, more than 200 individual measurements to build up this diagram. And always you have to switch on the oscillation. You have to wait for the transient time, and then you can measure, and then you switch on to the next measurement. It takes a long time to do that. There is a smarter way. I just tell you that. By using this signal, which is a changing oscillation, a so-called chirp, you can decompose this into different frequencies, and nearly all frequencies from nearly zero up to a certain maximum are covered with the same intensity. So you can excite with this signal all frequencies at once. And then you can also watch the sum of all answers or the responses to this input signal at once. So this makes the system much faster. And I think this is the actual method that the device is using, but that is just as a side information. Okay, these results are not by chance. We can also get by calculation there, but then we have to switch into complex calculations. Now, question: who knows about complex numbers? Okay, a lot? Not all, yeah, okay. You will need complex numbers. I think we cannot cover everything. So I would ask you to have a look at the background material. We have here in the Moodle course something about complex numbers. It sounds complex, it's not so bad. So we have here static material, background complex numbers. Here it's just some slides. And it shows our problem with the normal real numbers, that they have a limited number of solutions. So for a general way to solve equations, we need so-called complex numbers, which have a real part and another part which is just imaginary. So it's called the imaginary part. And then you can print numbers not only on a ruler, but you can print them on a plane. And you can calculate them with these numbers, which have some similar and some new laws in comparison to just real numbers. Okay. And let's then see in MATLAB what we can, how these complex numbers look like, especially when we say we have now an oscillation which is not just real, for example, a cosine or a sine. We have a complex oscillation, which means at any time we have a real part and an imaginary part of an amplitude. What is an imaginary part? Well, it's just something that you imagine. You can add it to the real part, which you can measure with a device, and the other one is just in your thoughts. And both together, that make up a complex signal. And why are we doing this? Well, it's just like a catalyst for a chemical reaction. It makes some calculations much easier. And after your calculation, you can drop the imaginary part and just work on the real signals, and then it will be the correct result. Okay, but we will have to take a look into these complex oscillations. And to see them, to understand them a little bit, let's already have a look in MATLAB. I didn't start this. Okay, I start MATLAB, and then we have approximately 30 minutes time. Oh, I tested this. I figured this. normally should open, and this is okay, but it looks now that the 30 minutes are starting, and let's see if we can do something more. The basis for a complex oscillation is a function, an exponential function with an imaginary part. Okay, wherever you see here a j, that means it's imaginary, and the exponential function with j omega t produces this oscillation. So the derivative of such a function is still an exponential function, just like for real values. But the first derivative, for example, here of a constant, okay, this y with a stroke below is just a constant, multiplied with this time function, e to the power of j omega t. Okay, the derivative here is just again this exponential function, but we have to multiply then with a factor, with the factor j omega. So instead of a complicated derivative, we have just a multiplication with a factor j omega. And well, you can see this is the first order differential equation. Okay, tau times the first derivative of something plus the same something yields k times the input oscillation. Okay, so this is the prototype of the first order oscillation. And the derivative becomes just a multiplication. So this now is just an algebraic equation, and you can multiply, divide, you can sort things. This is what makes it much easier to work with these complex oscillations. Okay, now let's see if we have now, yeah, we are here now. And then this looks like a coil in space. The coils around time axis, so the long axis here, this is time. And the frequency, we can change the frequency here, with the button here. I enlarge the frequency so we can see, okay, this coil becomes more tight. For example, for lower frequencies, there are lesser windings here. So, then we can take a look here in any direction how this looks like. Nice features, no? This is MATLAB. That's what we can do with MATLAB. We will not cover everything, but it's really fascinating. We can do the graphics here. Okay, so let's turn it around. What we can see is the long axis to the right, that's time again, and on the vertical axis we have now only the imaginary part, and this looks exactly like a sine. That means, and we could write it down, this function e to the power of j omega t contains an imaginary part, which always has a factor j, and a sine of omega t. And there's more. There's a third axis. This is the one here in front. So I try to revolve this around. So that the real axis, the real axis now is coming on top. So not perfectly, but we can see this is not a sine, this is a cosine. So that means for the real part, so this is the real part of this oscillation, this is the cosine. And that is what is contained in such a complex oscillation. The real part becomes an imaginary part. And you can see both of them also in this direction. Then the coil looks like a circle, and we have now just normal trigonometry here inside. On the horizontal axis we have real parts. These are imaginary parts. We're always moving here on this circle around. You see here a red button. You can change the position of this red button, and that means you change the time. Okay, so the starting time, and that means you change the phase. So we could add here a phase, and then you see the button moving, and we have here the so-called phase angle. Okay, that's the phase angle of a complex number, because what we see here is a complex amplitude. So the amplitude is not just one value, not just the radius of this circle, it includes the phase value. And okay, so this is always complex number, as I said, has always an absolute value, which is the radius, let's say r, multiplied with the phase angle. And actually, you can write it here with this notation, e to the power of j, and a phase angle. So r would be the radius, and phi is this phase angle. And we can see it still remains a coil in space, and when we change the phase every time, then we revolve a little bit around with this coil. Okay, so this is the complex oscillation, and we have seen its advantage when we use it in the differential equation, and the derivative looks like the original function, just with a factor here. If you would use a real function, a cosine for example, and you apply the derivative, well, the cosine becomes the sine, and this is a different function. You can still calculate with that, you know it probably from mathematics, but yeah, it's complicated to do that. And here, this is actually much easier. For example, now we have the output signal here in two positions, and it's, well, it's just the same signal here, just with a factor. And that means I can factor out this input signal and or this output signal, and I can calculate with this just like with any algebraic equation. So I can see here, okay, this is the output amplitude, and when I write it with a stroke below, it means it's not just the radius, it includes an amplitude. It includes the phase angle. Okay, that means this stroke. So the output amplitude, including this phase angle, multiplied with some factors, have something to do with the input amplitude. And we can even build a ratio between output and input amplitude. So, and this is normally a complex number. There's a real part and an imaginary part, or it has a radius and a phase angle. And in this case, well, this ratio is called the transfer function. And for this first order system, well, we get the amplification factor, the k, from the differential equation, the k on top, and in the denominator 1 plus j omega tau. This was the content of the round brackets here, and it contains the 1 stands for the one original output function, and the tau times j omega is tau times the first derivative of this output function. Okay, so this is still included here. So this was the first derivative once. Okay, in general, for different omegas, for different frequencies, a complex number. So it has an absolute value, a magnitude, and this is the ratio of amplitudes, the normal, real values of amplitudes. You can calculate it, okay, it's just the absolute value here of complex numbers, and the phase angles can also be calculated. So it's not just possible to measure these, you can also say, okay, this is mathematically defined, and when we plot this, it yields exactly the same diagrams as in the measurement. So this is not just by chance, this is true for every first order system. And not only for electric systems, not only for a circuit, it's also valid for a mechanical system, for example with a spring, just with a spring, or with a damper and things like that. Okay, for a second order system, we could do the same. So this comes from, where do we start? We have the output, then we have set 2 times d damping divided by this omega 0, multiplied with the first derivative. I write it with one stroke, plus 1 over omega 0 squared times the second derivative. And this was equal to some factor k times x. Using only complex oscillations, we can say here, okay, let's write a capital Y, that means it's just the amplitude of the output, not just the amplitude. And we have then 2d divided by omega 0 times, okay, first derivative means just j omega multiplied with the amplitude. And then we have the 1 over omega 0 squared. And a second derivative means just we have j omega squared. And then, of course, again, just the output amplitude, and this is equal to k times the input amplitude. And then on the left side, we have 3 times the y amplitude. We can factor this out. So we have y times 1 plus 2d. I write it a little bit different now, 2d multiplied with j omega divided by omega 0. And then the last term, j squared, okay, j is the imaginary unit, you can say j squared is minus 1. So we can replace this with a minus sign, and I do not write here a plus, I write a minus omega squared divided by omega 0 squared, okay, equals k times x. And sorry for my handwriting. And then you can see, okay, when we build now a ratio, the capital Y divided by capital X, that's our transfer function, is what remains then on the right side, just the k on top of a ratio, and the bracket becomes then the denominator. So it gets down here. This is exactly the content here of the round bracket. So that's where it comes from, and then we can just plot here the form here of the, by the way, it's called the Bode diagram. So this is the ratio of amplitudes, and these are the phase angles. And in this case, they change between 0 and minus 180 degrees. If you remember from the first order system, they change only between 0 and minus 90 degrees. So you have double the phase. Okay, but that's fine. Now, in system theory, not only in theory, but also in MATLAB, we use something which is called a Laplace transform. And this is not so worse as it sounds. This transfer function up to here, this is what we would call a Fourier transform. Okay, so a French guy called Fourier invented that. And important is, this is a function which depends on omega, but actually more on j times omega. Okay, it's a function of j times omega. And for some reasons, it's in many cases not enough to use this, so we use another variable, which is called the complex frequency, S. That's the Laplace variable S. For us, it's enough to know that normally you just replace wherever you find j omega in a transfer function, you replace this with S. Okay? So for example, first order system, we saw the transfer function is this ratio. We find a j omega here. We replace it with the letter S, and this would be then the Laplace transform, and this is what MATLAB takes. So we will see this next time when we see the introduction to MATLAB. It uses this Laplace form. So that's why I'm telling you this. One point where we have to be careful. Here is a minus omega squared, and we know that actually this means it's j omega squared, but it was here, so this was here a plus j omega squared. Okay, plus. And that's why we find also here then plus s by omega 0. So this is not an error, this must be mathematically like that. Okay, so that was system theory in short. I said at the beginning that we will also cover non-linear systems, and this Fourier and Laplace theory can be only used for linear systems. So if you have non-linearity, you can still describe it with a differential equation. It's possible, but you cannot use the Fourier or Laplace transforms. But in many cases, you can decompose the system into a static calculation from the input into some intermediate variable. And then time-dependent ones only between this intermediate variable and the output, which might be only linear. Then for the linear part, you can still use Fourier and Laplace transforms. You can use them in models in MATLAB. And for the first part, then this is just a formula, or it's just a characteristic where you get from one value to the next, but there is no dynamics in it. Okay, so this does not depend on time, or time dependencies are centered here. It's not always possible, but in many cases. Okay, so now we have covered a lot today. So next time we will then talk a little bit first about passive components, and then we start with the MATLAB introduction. So please remember that you install it on your computers. And now, if you didn't already have a nice lunch and a nice weekend, then you say okay. Thank you.
Also, you see, here, it is a your phone is